Look up at the night sky. See those stars, those distant galaxies captured by our most powerful telescopes. Every single point of light you've ever seen, every cosmic wonder ever photographed, every galaxy ever observed, all of it exists within a bubble. A finite sphere surrounding us in all directions. Beyond that sphere lies something we can never see, never touch, never observe, no matter how long we wait or how advanced our technology becomes. This isn't science fiction. This is the observable universe, and it has an edge. To understand why this boundary exists, we must first grasp a fundamental constraint that governs our view of the universe. The finite speed of light combined with the finite age of the cosmos itself. Light, despite being the fastest phenomenon in the universe, travels at a fixed speed of approximately 299,792 kilometers per second. While this seems extraordinarily fast by human standards, on cosmic scales it introduces a critical limitation. The universe itself is approximately 13.8 billion years old, having emerged from the Big Bang in an initial state of extreme density and temperature. This finite age means that light from extremely distant regions has only had 13.8 billion years to travel toward us. You might reasonably assume, then, that the observable universe would extend 13.8 billion light-years in every direction, creating a sphere with a radius of 13.8 billion light-years. However, the reality proves more complex and more fascinating than this simple calculation would suggest. The crucial factor that complicates this picture is cosmic expansion itself. The universe hasn't remained static since the Big Bang. Instead, space itself has been continuously expanding, carrying galaxies and other structures along with it. When light left a distant galaxy billions of years ago, heading in our direction, that galaxy was much closer to our location than it is now. During the billions of years that light traveled through space to reach our telescopes, the galaxy that emitted it has been carried farther away by cosmic expansion. This means that galaxies whose light has taken 13.8 billion years to reach us are now much farther away than 13.8 billion light-years. Through careful measurements and sophisticated cosmological models, astronomers have determined that the observable universe extends approximately 46.5 billion light-years in every direction from Earth, creating a sphere with a diameter of roughly 93 billion light-years. This colossal volume contains everything we can possibly observe, everything we have observed, and everything we ever will be able to observe using electromagnetic radiation. But why stop there? Why does this particular distance represent an ultimate limit? The answer lies not just in the past expansion of the universe, but in its ongoing and accelerating expansion today. Space isn't just expanding. In many regions, it's expanding at a rate that increases with distance. This creates a profound observational barrier that fundamentally limits what we can ever hope to see. The expansion of space presents one of the most counterintuitive concepts in modern cosmology, yet it's crucial for understanding why we face an observational horizon. Unlike objects moving through space, which are indeed limited by the speed of light, according to Einstein's theory of special relativity, space itself can expand at any rate. There's no cosmic speed limit on the expansion of space itself. This might sound like a violation of relativity, but it's actually perfectly consistent with Einstein's equations. Special relativity prohibits objects from moving through space faster than light, but it places no such restriction on the expansion of space itself. Imagine the universe as the surface of a balloon, with galaxies represented by dots marked on that surface. As you inflate the balloon, the dots move apart from each other, not because they're traveling across the rubber surface, but because the surface itself is stretching. No individual dot moves through the rubber faster than any cosmic speed limit, yet dots on opposite sides of the balloon can separate at enormous rates as the balloon expands. This analogy, while imperfect, captures the essential nature of cosmic expansion. At relatively nearby cosmic distances, expansion proceeds slowly enough that light from distant galaxies can make headway toward us, eventually reaching our telescopes despite the expanding space it must traverse. However, beyond a certain distance, the expansion rate becomes so great that light, even though it travels toward us at its maximum speed, makes no net progress in actually getting closer to our location. Space is expanding faster than the light can cross it, creating an effective horizon beyond which we cannot observe. Galaxies beyond this horizon recede from us faster than light can travel through the expanding space, rendering them forever invisible to us, no matter how long we wait or how sensitive our instruments become. This cosmic event horizon, as it's sometimes called, parallels in certain ways the event horizon of a black hole. Just as light cannot escape from within a black hole's event horizon, light from beyond our cosmic horizon cannot reach us. The difference is that a black hole's horizon is created by extreme gravitational warping of spacetime, while our cosmic horizon results from the expansion of space itself. In both cases, however, the result is an absolute observational boundary beyond which we cannot see. Current observations indicate that cosmic expansion is not just continuing, but accelerating, driven by a mysterious component we call dark energy. This acceleration means that our cosmic horizon is not merely a feature of looking into the past, but a permanent barrier that will persist into the future. In fact, the observable universe will actually shrink over vast cosmic timescales as more and more galaxies slip beyond our cosmic horizon, accelerated away by dark energy until their light can no longer reach us. But before we venture too far into speculation about what we cannot see, we must address what basic scientific reasoning tells us almost certainly exists beyond our observational boundary. The most straightforward and conservative assumption about what lies beyond the observable universe is simply that more of the same continues outward. This might sound unimaginative, but it's actually the assumption that requires the fewest additional hypotheses and best fits our observations. Every direction we look, out to the very edge of the observable universe, we see essentially the same thing: galaxies, clusters of galaxies, vast cosmic structures forming intricate webs, and the same laws of physics operating everywhere we can measure. The universe appears remarkably uniform at the largest scales we can observe. Consider what our telescopes reveal when we look at opposite sides of the sky, toward regions of space separated by the entire diameter of the observable universe. These regions are so distant from each other that light has never had time to travel between them since the Big Bang. They have never been in causal contact. No information or influence has ever passed from one to the other. Yet remarkably, they look essentially the same. Both contain similar densities of matter, similar types of galaxies distributed in similar patterns, and similar cosmic background radiation. This observation of large-scale uniformity suggests something profound about the universe beyond what we can see. If the observable universe were a special, unique region with distinctive properties, we might expect to see systematic differences between different parts of the sky, or at least some indication that we're observing the edge of something distinctive. Instead, we see consistency. Galaxies near the edge of the observable universe, seen as they were billions of years ago due to light travel time, look statistically similar to galaxies at various other distances. The cosmic microwave background radiation, which represents light from when the universe was only 380,000 years old, appears nearly identical in all directions, with temperature variations of only about 1 part in 100,000. This uniformity suggests that the universe doesn't simply stop at the edge of what we can observe, but continues onward with more galaxies, more stars, more structure. Think of it this way. Imagine you're in a vast forest and fog limits your vision to a circle 100 meters in radius. Everywhere you look within that circle, you see similar trees, similar undergrowth, similar terrain. Would you conclude that the forest ends precisely at the edge of your visibility? Or would you reasonably infer that the forest continues beyond what you can see? The principle is the same with the observable universe. We see no evidence of an edge, no indication of fundamental differences between nearby and distant regions, no suggestion that the universe's character changes at the limits of our observation. This reasoning is formalized in cosmology through what's called the cosmological principle, one of the fundamental assumptions underlying modern cosmology and our understanding of the universe's large-scale structure. The cosmological principle asserts that the universe is both homogeneous and isotropic at sufficiently large scales. Homogeneity means that the universe has essentially the same properties at every location. There's no special center or edge. Isotropic means that the universe looks the same in every direction. There are no preferred directions in space. Together, these properties imply that our position in the universe is not privileged or special. An observer in a galaxy 10 billion light-years from Earth would see their own observable universe centered on their location that looks fundamentally similar to ours. The evidence supporting the cosmological principle comes from multiple sources. The cosmic microwave background radiation provides perhaps the most compelling support. This radiation, the afterglow of the Big Bang itself, fills all of space and has been traveling through the universe for over 13.8 billion years. Detailed measurements by satellites such as COBE, WMAP, and Planck have mapped this radiation with exquisite precision, revealing that it has nearly identical temperature in all directions, approximately 2.725 Kelvin. The tiny variations that do exist, those temperature fluctuations of 1 part in 100,000, are distributed across the sky in a pattern that shows no preferred orientation or location. This remarkable uniformity indicates that the early universe was extraordinarily homogeneous and isotropic, with no special locations or directions. Furthermore, when we survey the distribution of galaxies across vast cosmic volumes, we find that while significant structure exists at smaller scales, gravitationally bound galaxy clusters, vast filaments, and walls of galaxies, enormous voids containing few galaxies, the statistical properties become increasingly uniform as we examine larger volumes. On scales of roughly 300 million light-years and greater, the distribution of matter becomes statistically uniform. One huge cubic volume of space contains, on average, the same amount of matter and the same types of structures as another similar volume elsewhere in the observable universe. This principle has profound implications for what lies beyond our cosmic horizon. If the cosmological principle holds true, and all evidence suggests it does, then regions beyond our observable universe should contain more of the same. More galaxies forming clusters and superclusters. More stars being born and dying. More planets orbiting those stars. More black holes. More of everything we observe within our cosmic sphere. Moreover, the laws of physics should remain the same out there. The speed of light, the strength of gravity, the behavior of atoms and subatomic particles. All should operate by the same rules in those forever invisible regions. Consider an observer in a galaxy at the very edge of our observable universe, some 46 billion light-years away from Earth as it exists now. That observer would see their own observable universe, a sphere of the same size, centered on their location. Only a small portion of their observable universe would overlap with ours. Most of what they can see, we cannot, and most of what we see, they cannot. Yet the cosmological principle suggests their view would be statistically indistinguishable from ours. They would see galaxies, stars, planets, and cosmic structure arranged differently in specific details, but following the same patterns and laws. Extending this logic, we can imagine a chain of observers, each at the edge of the previous observer's observable universe. An observer at the edge of that second observer's view would see yet another region of space, even more distant from us, that we could never observe even indirectly. If we continue this chain indefinitely, we conceptualize an universe extending far beyond what we can see, potentially without limit. This leads us to questions about the minimum and potentially maximum extent of the universe beyond our horizon. Questions that observations of the cosmic microwave background begin to address. Measurements of the cosmic microwave background don't just tell us that the universe is uniform. They also provide information about the shape and minimum size of the universe as a whole. One of the most important properties we can measure from the CMB is the curvature of space itself. General relativity tells us that space can have positive curvature, like the surface of a sphere, negative curvature, like a saddle shape, or zero curvature, meaning it's perfectly flat like an infinite plane. The curvature of space affects the apparent size of features in the cosmic microwave background. Think of it this way. If you draw a circle on a flat piece of paper, its circumference equals 2 times pi times its radius, exactly as Euclidean geometry predicts. However, if you draw a circle on the surface of a sphere, its circumference is less than 2 pi times the radius measured along the sphere's surface. Conversely, on a negatively curved saddle-shaped surface, a circle's circumference exceeds 2 pi times its radius. Similarly, the apparent angular size of features in the CMB depends on the curvature of the space through which their light has traveled to reach us. Remarkably, precise measurements of the CMB reveal that space is flat, or very close to flat, to within observational uncertainties. The latest data indicates that if space is curved at all, the radius of curvature must be at least hundreds of times larger than the observable universe itself. This flatness has profound implications. If space is perfectly flat, as the data suggests, then the universe could be infinite in extent, continuing forever in all directions. Even if space has a slight curvature below our current ability to detect, the universe must still be vastly larger than the region we can observe. Additionally, certain patterns in the cosmic microwave background provide information about the minimum size of the universe. The CMB shows temperature fluctuations at various angular scales, creating a characteristic power spectrum that reveals information about acoustic oscillations in the early universe, essentially sound waves in the primordial plasma. If the universe were only slightly larger than our observable region, we would expect to see suppression of the larger scale fluctuations in the CMB, because there wouldn't be room for larger waves. The absence of this suppression, along with theoretical considerations from inflation theory, indicates the universe must extend far beyond what we can observe. Different analyses using various assumptions yield different minimum sizes, but most suggest the entire universe is at least 250 times larger than the observable universe in all directions, possibly much larger, potentially infinite. To put this in perspective, if the universe is 250 times larger in radius than the observable portion, it would contain roughly 15 million times more volume. If each cubic volume, similar in size to our observable universe, contains a similar amount of matter, the total amount of matter in just this minimum size universe would be staggering beyond human comprehension, vastly exceeding the roughly 2 trillion galaxies estimated to exist in the observable universe alone. But what if the universe is even larger than this minimum? What if the universe extends infinitely in all directions, containing infinite matter and infinite space? This possibility, far from being mere speculation, represents a legitimate scientific hypothesis consistent with our best observations and theories. An infinite universe presents conceptual challenges to our intuition, yet remains perfectly compatible with physics and mathematics. Infinity appears frequently in mathematics and physics. Mathematicians work with infinite sets, infinite series, and infinite spaces routinely. In physics, various quantities can in principle take infinite values, and many models invoke infinite space or time. The question is whether our particular universe, the one we inhabit, is actually infinite or merely enormously large. If the universe is truly infinite, it contains infinite volume, infinite matter, and infinite energy. An infinite universe would contain infinitely many galaxies, infinitely many stars, infinitely many planets. Every possible arrangement of matter that doesn't violate physical laws would exist somewhere, simply because there's infinite space in which it could occur. This has some truly bizarre implications, which we'll explore shortly. But first, it's worth emphasizing that an infinite universe poses no logical contradictions or physical impossibilities. One common question about an infinite universe is whether it could have emerged from the Big Bang, which we often visualize as everything expanding from a single point. The key is understanding what the Big Bang actually was. The Big Bang wasn't an explosion of matter into empty space from a single point. Rather, it was an explosive expansion of space itself, occurring everywhere simultaneously. If the universe is infinite now, it was also infinite at the time of the Big Bang, just much denser. During the Big Bang and the subsequent expansion, every region of space grew farther apart from every other region. But if space was infinite to begin with, it remained infinite even as it expanded and cooled. Imagine an infinite grid stretching in all directions. If you double the spacing between all grid points, you still have an infinite grid, just less dense. This captures the essence of how an infinite universe can expand. There's no center from which expansion proceeds, and no edge toward which it expands. Every point moves away from every other point, but the universe as a whole remains infinite before, during, and after the expansion. In an infinite universe, there would exist countless other regions like our observable universe, each centered on a different location in space. These regions would overlap partially with ours, but each would extend into territories we can never observe. An observer in one of these distant regions would see their own 93 billion light-year diameter sphere of observable space, most of which would be forever beyond our observation, just as most of our observable universe lies beyond theirs. Picture the universe as an infinite three-dimensional space, with observable universe regions scattered throughout like overlapping spheres of light in an infinite darkness. Each sphere represents what can be observed from that particular vantage point. These spheres overlap where their boundaries intersect, creating regions visible from multiple locations. But each sphere also contains vast volumes unique to its particular viewpoint. In an infinite universe, infinitely many such spheres exist, creating an infinite patchwork of overlapping observable regions. This patchwork has a strange implication. There exist regions of space so distant from us that not only can we never observe them, but no information from our region can ever reach them, and no information from their region can ever reach us. We exist in fundamentally separate, causally disconnected regions of the same universe. Events happening in those regions now have no effect on us and never will. Similarly, nothing occurring in our region now can ever affect them. They are, in every practical and physical sense, separate universes despite existing in the same continuous space. Yet, if we push the implications of an infinite universe further, we encounter something even more unsettling: the inevitability of repetition. This emerges from a simple, logical argument based on infinity and finite possibilities. Consider any finite volume of space, say a cube 1 meter on each side. This volume can contain only a finite number of fundamental particles, limited by the quantum exclusion principle and the finite amount of energy available. Each of these particles can have only a finite number of possible quantum states. Therefore, the total number of possible arrangements of particles within that cubic meter is enormous, but ultimately finite. The same applies to any finite volume, whether a cubic centimeter or a volume encompassing an entire galaxy. Now, if the universe is truly infinite, it contains infinitely many such volumes. But if each volume has only a finite number of possible configurations, and we have infinitely many volumes, then by the pigeonhole principle, mathematical logic dictates that configurations must repeat. In fact, they must repeat infinitely many times. Every possible arrangement that can occur in a given volume must occur infinitely often throughout an infinite universe. This applies not just to simple arrangements of particles in small volumes, but to arbitrarily large volumes as well. Consider a volume large enough to contain the entire Milky Way galaxy. This volume, while staggeringly large by human standards, is still finite. The number of possible arrangements of all the particles in such a volume is incomprehensibly large, but still finite. In an infinite universe, this finite number of possibilities must be exhausted, and beyond that point, arrangements must begin repeating. Taking this to its logical extreme, consider a volume large enough to contain Earth, our solar system, our galaxy, and all nearby cosmic structure. Somewhere in an infinite universe, an exact duplicate of this entire region must exist. Not just similar, but identical down to the quantum state of every particle. This duplicate region would contain an exact copy of Earth, with exact copies of all its history, all its geology, all its life, and all its people. There would be a duplicate you, with the same memories, the same thoughts. Reading these same words at this same moment, this conclusion seems absurd, yet it follows logically from the premises of an infinite universe and finite possible states. Of course, there are subtleties and assumptions involved. Quantum mechanics introduces fundamental randomness that might affect whether exact duplication is truly inevitable. The nature of infinity itself involves mathematical subtleties that might complicate the simple pigeonhole argument. Nevertheless, the basic point remains. An infinite universe with finite possible states per volume implies repetition on cosmic scales. These duplicates would be extraordinarily far away, vastly beyond our observable universe. The number of possible quantum states in a volume the size of Earth's observable region is so enormous, roughly 10 to the power of 10 to the power of 124 according to some estimates, that you would need to search through an incomprehensibly vast amount of space before finding an exact duplicate. But in an infinite universe, such duplicates exist, infinitely many of them. More unsettling still, every possible variation that doesn't violate physical laws would also exist somewhere. Regions almost identical to ours, but with small differences. Versions of Earth where history diverged at some point. Versions of you who made different choices. Every possible outcome of every quantum event, every possible arrangement of matter consistent with physical law, realized somewhere in the infinite expanse. This might sound like science fiction, but it emerges naturally from taking seriously the possibility that the universe is infinite and applying straightforward logical reasoning. Of course, we can never observe these duplicates or variations. They lie far beyond our cosmic horizon, but their theoretical existence raises profound questions about identity, uniqueness, and the nature of reality itself. There is, however, an alternative to an infinite flat universe that avoids these strange repetition implications while still being consistent with observations. The universe could have an unusual topology. In everyday experience, we think of space as having simple, Euclidean geometry extending infinitely in all directions. However, general relativity and modern cosmology allow for more exotic possibilities. Space could be finite, yet unbounded, having no edge but still containing a limited volume. The classic analogy is the surface of a sphere, which is finite in area but has no boundary or edge. If you travel in one direction on a sphere's surface, you eventually return to your starting point. The universe could have a similar property in 3 dimensions. Various specific topologies have been proposed for the universe. One is the 3 torus, essentially a 3-dimensional version of a torus or donut shape. In a 3 torus universe, if you traveled far enough in any of 3 perpendicular directions, you would eventually return to your starting point, like a 3-dimensional version of the classic video game Pac-Man, where going off one edge brings you back on the opposite edge. Such a universe would be finite in volume, but would have no boundary, no edge beyond which you cannot travel. Another proposed topology is the Poincaré dodecahedral space, named after mathematician Henri Poincaré. This involves a dodecahedron, a 12-sided solid, with its opposite faces identified in a specific way. A 3-dimensional traveler leaving through one face would enter through the opposite face. This creates a closed, finite space with no boundary. These exotic topologies would have observable consequences in the cosmic microwave background. If the universe had such a topology and were small enough, we might see repeated patterns in the CMB, essentially looking at the same regions of the early universe from multiple directions as light wrapped around the topology. Cosmologists have searched for such patterns and found no convincing evidence, which places lower limits on how small the universe could be if it has an unusual topology. The universe must be at least larger than our observable region, and probably much larger, even if it has a complex topology. Nevertheless, the universe could have an exotic topology that's simply too large for us to detect with current observations. In such a scenario, the universe would be finite, but enormously large, possibly thousands or millions of times larger than the observable portion. This would avoid the infinite repetition problem while still placing the vast majority of the universe beyond our cosmic horizon. The question of whether the universe is infinite or merely extremely large but finite remains open. Current observations cannot definitively distinguish between these possibilities. What we can say is that the universe extends far beyond what we can observe, and that its full extent may be vastly larger than the already enormous observable portion. But the possibilities for what lies beyond become even more exotic when we consider theories that go beyond simple spatial continuation and introduce the concept of multiple bubble universes. The theory of cosmic inflation, proposed in the early 1980s to solve several problems in Big Bang cosmology, suggests that the early universe underwent a period of extraordinarily rapid expansion. During a tiny fraction of a second, shortly after the Big Bang, space expanded exponentially, doubling in size every 10 to the negative 37 seconds or so. This inflation lasted perhaps 10 to the negative 32 seconds. But during that brief moment, the universe expanded by an enormous factor, possibly increasing in size by more than 10 to the power of 26 times. Inflation solves several cosmological puzzles, including why the universe is so uniform and flat, but it also has a remarkable implication. Our observable universe, and indeed far more than we can observe, represents just a tiny region where inflation ended. The inflating space was quantum mechanical in nature, subject to quantum fluctuations. In some regions, these fluctuations caused inflation to end, allowing normal expansion and the evolution we observe. But in other regions, inflation continued. Here's where it gets interesting. Once inflation starts, it's very hard to stop everywhere at once. Quantum fluctuations ensure that while inflation ends in some regions, creating bubble universes, it continues in others. Moreover, the regions where inflation continues expand so rapidly that they create more and more space in which new bubbles can form. This leads to a process called eternal inflation, where inflation never ends globally, even though it ends locally in bubble regions. Our observable universe would be one such bubble, or more precisely, a tiny portion of one bubble. The entire region where inflation ended in our local area might be vastly larger than what we can observe, possibly infinite itself. But beyond that region, inflation continues. And within that eternally inflating space, countless other bubbles form, each potentially representing its own universe with its own properties. These bubble universes would be separated by regions of inflating space. Since space within the inflating regions expands faster than light, bubbles can never make contact with each other. Each bubble is causally disconnected from all others, existing in its own separate domain of space and time. An observer within one bubble cannot see or interact with other bubbles. They lie beyond that bubble's cosmic horizon, just as surely as distant regions of our own universe lie beyond ours. This scenario, if correct, means that what lies beyond our observable universe is not just more of the same universe, but potentially first more of our own bubble, extending far beyond what we can see, and eventually the boundaries of our bubble beyond which inflation continues and other bubbles exist. The multiverse suggested by eternal inflation is not just different observable regions of the same space, but genuinely separate universes, each with potentially different properties. Eternal inflation emerges naturally from most versions of inflation theory once you take quantum mechanics into account. The inflaton field, the hypothetical field driving inflation, is subject to quantum fluctuations. In some locations, these fluctuations cause the field to decrease, ending inflation and allowing a normal universe to form. But in other locations, the fluctuations cause the field to increase, causing inflation to continue even more vigorously. The key insight is that the inflating regions expand so rapidly that even though some parts stop inflating and become bubble universes, the total volume of inflating space increases. It's like a fractal foam, with bubbles constantly forming within an eternally growing inflating background. Each bubble represents a universe, potentially infinite in extent itself, but surrounded by inflating space containing countless other bubbles. The mathematics of eternal inflation suggests this process, once started, continues forever into the future and may have been ongoing eternally into the past. New bubbles constantly form, each potentially containing trillions of galaxies and providing a home for 13.8 billion years of cosmic evolution like our own. The number of such bubbles would be unlimited, constantly increasing, creating an infinite multiverse of bubble universes within an eternally inflating space. This scenario has a profound implication. Different bubbles might have different physical properties. The fundamental constants of nature, which we measure within our bubble, might vary from bubble to bubble. When inflation ends in a particular region, the inflaton field decays, converting its energy into particles and radiation. This process, called reheating, sets the initial conditions for that bubble universe. But the precise way this happens might differ between bubbles. The vacuum state of various quantum fields might settle into different configurations, leading to different effective physical laws. String theory, a theoretical framework attempting to unify quantum mechanics and general relativity, suggests there might be an enormous number of possible vacuum states, called the string theory landscape. Estimates suggest perhaps 10 to the power of 500 different possible vacuum states, each corresponding to different values of fundamental constants and perhaps even different particles and forces. If eternal inflation is correct and the string landscape is real, different bubbles might sample different regions of this landscape. One bubble might have a slightly stronger electromagnetic force, another might have heavier quarks, a third might have additional spatial dimensions that haven't compactified in the same way. The possibilities are staggering in their variety. Most of these possibilities would create universes hostile to life as we know it. If the electromagnetic force were much stronger, atoms couldn't form. If the strong nuclear force was slightly different, atomic nuclei might be unstable. If the mass of the electron differed significantly, chemistry as we know it would be impossible. The vast majority of possible combinations of physical constants would create universes that are empty, boring, or actively hostile to complex structures. But with infinitely many bubbles sampling different possibilities, even vanishingly rare combinations that allow life would occur infinitely many times. And this leads to an important consideration: the anthropic principle and why we find ourselves in a universe with properties amenable to life. The anthropic principle, in its simplest form, states that we observe the universe to have properties compatible with our existence because we couldn't observe it otherwise. This might sound tautological, but it has genuine explanatory power in a multiverse scenario. If countless bubble universes exist with varying properties, and only a tiny fraction have properties allowing complex chemistry, stable stars, and thus potentially life and observers, then we naturally find ourselves in one of the rare bubbles with suitable conditions. This provides a potential explanation for what seems like remarkable fine-tuning in our universe. Many physical constants appear to sit in narrow ranges that allow for interesting chemistry and complex structures. If any were significantly different, the universe would be unable to support life. Traditionally, this apparent fine-tuning has been seen as either requiring explanation through some deeper physical principle or interpreted as evidence for design. The multiverse offers a third option. No deeper principle is needed, and no design is required. If all possible values of constants are realized in different bubbles, and observers can only exist in bubbles with suitable values, then the apparent fine-tuning is explained through selection bias. We observe a life-friendly universe, not because all universes are life-friendly, but because we couldn't find ourselves in any other type. This anthropic explanation remains controversial among physicists and philosophers. Some argue it's unscientific because it invokes unobservable entities, other bubble universes to explain features of the one universe we can observe. Others counter that if eternal inflation and the string landscape are true, the multiverse is a prediction of our best theories, not an ad hoc invention. The debate continues, touching on fundamental questions about what constitutes a scientific explanation. Regardless of its merit in explaining fine-tuning, the anthropic principle highlights an important point. If multiple universes exist with different properties, the properties we observe may not be fundamental or necessary, but simply the properties compatible with our existence as observers. The string theory landscape mentioned earlier deserves deeper exploration. String theory proposes that fundamental particles aren't point-like, but rather tiny vibrating strings. Different vibration modes of these strings correspond to different particles and forces. For the mathematics to work, string theory requires additional spatial dimensions beyond the 3 we experience, possibly 6 or 7 extra dimensions. These extra dimensions must be compactified, curled up into tiny spaces too small to observe directly. The specific way they compactify, their shape and size, determines the effective physical laws in the resulting 4-dimensional universe. Different compactification geometries lead to different particle content, different forces, and different values of constants. The number of possible compactification geometries is astronomical. Early estimates suggested perhaps 10 to the power of 500 different possibilities, though this number is uncertain. Each represents a different vacuum state, a different stable configuration of the quantum fields pervading space. Each would create a universe with potentially different physics. In the context of eternal inflation, different bubble universes might settle into different points in this landscape. Our bubble occupies one particular point, with one particular compactification geometry giving rise to the particles and forces we observe. Other bubbles occupy other points, experiencing different physics. Some regions of the landscape might be more common than others, if certain vacuum states are easier to reach from the initial conditions of bubble formation. But with infinitely many bubbles, even extraordinarily rare configurations would occur infinitely many times. Every possible point in the landscape would be realized in some bubble universe somewhere in the eternally inflating multiverse. This landscape picture suggests breathtaking diversity among bubble universes. Some might have only electromagnetic and gravitational forces. Others might have entirely different types of forces unknown in our universe. Some might have different numbers of stable particles. The variety would be truly endless, limited only by the mathematical structure of string theory itself. Of course, string theory remains unproven and controversial. Despite decades of research, no experimental evidence confirms it, and theoretical challenges persist. The landscape itself is controversial, even among string theorists. But if string theory is correct and the landscape real, and if eternal inflation occurs, then what lies beyond our cosmic horizon includes not just more space, but other universes with radically different properties, representing different solutions to the fundamental equations of physics. There's yet another type of multiverse worth considering, one that doesn't rely on spatial separation at all, but emerges from quantum mechanics itself, the many worlds interpretation. Quantum mechanics, our best theory of physics at microscopic scales, describes reality in terms of probability amplitudes. When we measure a quantum system, such as the spin of an electron, quantum mechanics doesn't predict a definite outcome, but rather probabilities for different outcomes. The standard interpretation suggests that measurement causes the quantum state to collapse randomly to one of the possible outcomes. with probabilities given by quantum theory. The many worlds interpretation proposed by Hugh Everett in 1957 offers a radical alternative. It suggests that all possible outcomes of every quantum measurement actually occur, but in different branches of reality. When you measure an electron's spin, the universe splits into two branches, one where you observe spin up, and one where you observe spin down. Both outcomes happen, but in separate non-interacting branches of the quantum wave function. This splitting happens constantly, at every quantum event throughout the universe. Each possible outcome of each quantum process creates a new branch. The result is a vast, continuously branching tree of parallel realities, all equally real, containing every possible history consistent with quantum mechanics. In this quantum multiverse, what lies beyond our observable universe is not just other regions of space or other bubble universes, but other branches of quantum reality. There exist parallel versions of you reading this, making slightly different choices, experiencing different sequences of quantum events. In some branches, historical events went differently because random quantum events had different outcomes. In others, quantum fluctuations in the early universe created entirely different distributions of galaxies. The many worlds interpretation remains controversial and is not universally accepted by physicists. It requires accepting that reality consists of an enormous, perhaps infinite number of parallel branches, almost all of which we can never observe or interact with. Critics argue this is extravagant, multiplying entities beyond necessity. Proponents counter that it's the simplest interpretation that takes quantum mechanics seriously, accepting its mathematics at face value without adding extra assumptions about wave function. Collapse. If the many worlds interpretation is correct, then what lies beyond our experience includes not just distant spatial regions or other bubble universes, but parallel quantum branches layered upon our own spacetime. Every possible quantum history is realized somewhere in the quantum multiverse. Interestingly, the quantum multiverse and the inflationary multiverse might both exist simultaneously. Eternal inflation creates separate bubble universes in different regions of space, while quantum mechanics creates parallel branches within each bubble. The full structure of reality would then include spatial bubbles, each containing a branching tree of quantum realities, all embedded within an eternally inflating background. The complete multiverse would be almost impossible to visualize, combining spatial separation, quantum branching, and potentially different physical laws in different regions. Yet all of these scenarios, from simple spatial continuation to exotic multiverses, share a common feature. They make claims about regions of reality we cannot observe. This raises profound questions about testability, scientific methodology, and the boundaries of legitimate scientific inquiry. Science traditionally relies on empirical observation and testability. We propose theories, derive predictions from those theories, and test the predictions against observations. Theories that make correct predictions are provisionally accepted. Those that fail are modified or rejected. This process has proven enormously successful over centuries, building our modern understanding of nature. But what happens when theories make claims about regions that are, in principle, unobservable? Do such claims remain scientific, or do they venture into metaphysics and philosophy? The question of what lies beyond the observable universe presents exactly this challenge. By definition, we cannot observe these regions directly. No light from beyond our cosmic horizon can reach us. No information can cross the boundary imposed by cosmic expansion. Any claim about what exists there seems immune to direct empirical testing. Does this mean such claims are unscientific? Many philosophers of science and some physicists argue yes, that claims about unobservable regions do not constitute legitimate science. They maintain that science must restrict itself to testable claims about the observable world. Speculations about other universes, whether separated by space or by quantum branching, may be interesting philosophical exercises, but they're not science in the traditional sense. This perspective emphasizes falsifiability, the criterion proposed by philosopher Karl Popper. A claim is scientific only if we can conceive of observations that would prove it false. Claims about forever unobservable regions fail this test. Others defend the scientific legitimacy of such claims by pointing out that we infer unobservable entities routinely in science. We cannot directly observe electrons, quarks, or black hole interiors, yet we accept their existence because theories involving them make testable predictions about what we can observe. Similarly, eternal inflation, the landscape of string theory, and even the simple continuation of space beyond our horizon are not arbitrary speculations, but predictions of theories developed to explain observable phenomena. Inflation theory, for instance, was developed to solve specific problems with standard Big Bang cosmology. Why the universe is so uniform, why space is so flat, why we don't observe certain exotic relics predicted to form in the early universe. The theory successfully explains these observations, and eternal inflation emerges naturally when we apply quantum mechanics to inflation. We didn't invent eternal inflation to explain fine-tuning. Rather, it's a consequence of a theory accepted for other reasons. If that theory predicts other bubbles, those bubbles are as much a part of the theory's implications as its explanations of observables. Furthermore, some argue that even claims about unobservable regions might have indirect observable consequences. The total size of the universe might affect the largest scale patterns in the cosmic microwave background. The topology of space might create subtle correlations in the CMB if the universe is finite and wrapped. The quantum multiverse might have testable implications through quantum interference experiments or the solution to measurement problems in quantum mechanics. While we cannot observe other bubbles directly, the theory that predicts them might make other testable predictions. The debate over testability and scientific legitimacy remains unsettled. What's clear is that modern cosmology increasingly confronts the boundaries of observability, forcing scientists to grapple with questions about what constitutes acceptable scientific reasoning. These are not merely academic debates. They touch on fundamental questions about knowledge, reality, and the scope of human understanding. Regardless of philosophical debates about testability, scientists continue searching for ways to learn more about what lies beyond our observable universe through improved observations within it. Future measurements may not show us directly what's beyond our horizon, but they could constrain the possibilities and provide evidence for or against various scenarios. The cosmic microwave background remains one of the most promising sources of information. Current measurements have characterized it with impressive precision, but future experiments aim to do even better, particularly measuring the polarization of the CMB radiation with greater sensitivity. This polarization contains information about gravitational waves from the early universe, ripples in spacetime itself produced during cosmic inflation. Detecting these primordial gravitational waves would provide strong evidence for inflation and might reveal details about how inflation proceeded, which could in turn constrain whether eternal inflation occurs. Additionally, more precise measurements of the CMB temperature and polarization patterns might reveal subtle features indicating the universe's total size or topology. If the universe has an unusual topology and is only slightly larger than the observable region, we might detect repeating patterns where we see the same structures from multiple directions. Alternatively, if the universe is truly infinite, but certain patterns in the CMB are suppressed or enhanced, this could tell us about physical processes operating on scales larger than we can directly observe. Gravitational wave astronomy, inaugurated with the direct detection of gravitational waves in 2015, offers another window. While current detectors observe waves from relatively nearby astrophysical sources like merging black holes and neutron stars, future space-based detectors might detect lower-frequency gravitational waves from the early universe. These could carry information about cosmic inflation, phase transitions in the early universe, or other processes that occurred on scales larger than our current observable region. The distribution of galaxies and large-scale cosmic structure also contains information about the early universe. By mapping the positions and motions of millions of galaxies, astronomers can reconstruct the pattern of tiny density variations that existed in the early universe, which later grew through gravity into the galaxies and clusters we see today. These patterns are influenced by the total size and shape of space, providing another indirect probe of what lies beyond our observation. Particle physics experiments might even contribute. If string theory is correct and the landscape real, high-energy particle collisions might reveal signatures of the extra dimensions or aspects of the vacuum structure our universe occupies. While this wouldn't tell us directly about other bubbles, it would confirm the theoretical framework that predicts them. None of these observations will let us directly see beyond the cosmic horizon. That remains impossible by definition. But they can test the theories that make predictions about what's beyond, providing evidence that makes certain scenarios more or less plausible. Science progresses not always by direct observation of everything we want to know about, but by testing theories that make claims extending beyond immediate observation. Looking forward not just in terms of better observations, but in terms of cosmic time itself, we must consider how what we can observe will change over billions of years due to the universe's ongoing expansion and the effects of dark energy. Dark energy, the mysterious component causing cosmic expansion to accelerate, currently dominates the universe's energy budget. Its effect causes distant galaxies to recede from us at ever-increasing rates. While galaxies relatively near to us, within our local supercluster, remain gravitationally bound and won't recede, more distant galaxies will continue accelerating away. Eventually, they'll cross beyond our cosmic horizon, their light forever unable to reach us as space between us and them expands faster than light can traverse it. Over the next 100 billion years, if dark energy remains constant, more and more galaxies will slip beyond our horizon. Distant galaxy clusters visible today in our most powerful telescopes will fade and disappear, their light redshifted into undetectability before vanishing entirely. The observable universe will shrink, not in absolute size, but in the amount of content it reveals. Eventually, in the far future, perhaps 150 billion years from now, observers in the Milky Way, or whatever galaxy results from our merger with Andromeda and other local galaxies, will see an observable universe containing only their own local gravitationally bound structure. Everything else will have receded beyond the horizon. The cosmic microwave background itself will be redshifted to such long wavelengths and diluted to such low temperatures that it becomes undetectable. Evidence of the Big Bang, evidence of cosmic expansion, evidence that the universe is anything more than our local cluster of galaxies. will all disappear beyond observability. These future observers, if they exist and contemplate the cosmos, will face a profound challenge. All the evidence we have today for the Big Bang, for the age of the universe, for the existence of billions of other galaxies, will be gone, carried away by expansion. If they develop cosmology from scratch, based only on what they can observe, they might conclude they inhabit a static, eternal universe consisting only of their local galaxy in an infinite empty void. They would be profoundly mistaken, yet their error would be justified by the evidence available to them. This far future scenario has a humbling implication for us today. Are we perhaps in an analogous situation? Might we be missing crucial evidence about the universe's nature because that evidence has already expanded beyond our horizon? Events in the universe's past, structures that existed long ago, might have receded from observability before we evolved to observe them. We could be fundamentally mistaken about aspects of cosmic history or structure, not through any failure of reasoning or observation, but simply because the evidence is no longer accessible. This brings us back to questions about information and what it means for something to exist, if we can never observe it or be influenced by it in any way. These questions sit at the intersection of physics and philosophy, touching on fundamental issues about reality and knowledge. Consider a galaxy that exists beyond our cosmic horizon. Light from that galaxy can never reach us. No information about it can ever influence anything in our observable region. In what sense can we say it exists? Clearly, if our theories are correct and the universe continues beyond our horizon, that galaxy exists as much as galaxies we can observe. But its existence has no operational consequence for us. We cannot see it, we cannot visit it, we can never know anything specific about it. Some physicists and philosophers argue that if information about something can never reach us, even in principle, then discussing its existence becomes meaningless from our perspective. This position, related to operationalism in philosophy of science, suggests we should only concern ourselves with entities and properties that can, at least in principle, be measured or observed. Anything permanently beyond observation lies outside the scope of physics. Others maintain that reality exists independently of our ability to observe it. The fact that we cannot see beyond our cosmic horizon doesn't mean nothing exists there. It merely means we cannot know what exists there. This position, closer to philosophical realism, asserts that the universe has properties and contains structures regardless of whether any observer can measure them. The question connects to long-standing debates in quantum mechanics about the role of observation and measurement in determining reality. Some interpretations of quantum mechanics suggest observation plays a fundamental role in bringing properties into existence. Others, like the many worlds interpretation or hidden variable theories, maintain that reality exists in definite states regardless of observation. The debate about regions beyond our observable universe parallels these quantum debates, raising questions about the relationship between existence, observation, and information. From an information theoretic perspective, physics is fundamentally about information. What can be known, what can be measured, how information propagates through space and time. Events beyond our cosmic horizon constitute information that can never propagate to us, raising questions about whether such information exists in any meaningful sense for us. Yet the theories we use to understand our observable universe naturally predict that such regions exist, even if we cannot verify their specific properties. These are not questions physics alone can answer. They require engagement with philosophy, epistemology, and metaphysics. They remind us that science despite its extraordinary success in explaining and predicting observable phenomena, faces limits when confronting questions about unobservable reality. This doesn't invalidate scientific theories that make predictions about unobservable regions. Rather, it highlights that interpreting those theories and deciding what to believe about their implications involves judgments that go beyond pure empiricism. As we contemplate what lies beyond the observable universe, we're forced to acknowledge that this question represents perhaps the deepest mystery in cosmology. It sits at the ultimate boundary of scientific inquiry, where physics meets philosophy, where observation ends and speculation begins, where our most sophisticated theories make their boldest claims precisely where verification becomes impossible. We've explored multiple possibilities for what might lie beyond our cosmic horizon. The most conservative is simple continuation: more galaxies, more stars, more structure, extending perhaps infinitely in all directions with the same physical laws operating throughout. This requires no exotic new physics, just acceptance that the universe is larger than what we can see. Observations of uniformity in the cosmic microwave background and the large-scale distribution of matter support this view. The cosmological principle, the assumption that our location is not special, suggests that observers anywhere in the universe would see similar phenomena. If the universe is infinite, it contains infinite matter and energy, with the strange implication that all possible configurations must repeat infinitely often at sufficient distance. Alternatively, the universe might be finite, but with unusual topology, wrapped back on itself in ways that create a closed space without boundaries. A three-torus, Poincare dodecahedral space, or other exotic topology would make the universe finite while avoiding any edge. Such topologies must be large, at least larger than our observable region, or we would have detected their signatures in the cosmic microwave background. But they could be vastly larger, making the universe enormous but not infinite, with no repetition problem. More exotically, eternal inflation suggests our observable universe is a tiny bubble in a vast inflating space that spawns countless other bubbles, each potentially a universe unto itself. These bubble universes would be causally disconnected from ours, existing beyond our cosmic horizon in regions still undergoing inflation. If the string theory landscape is real, different bubbles might sample different vacuum states, leading to different physical constants or even different fundamental forces. This inflationary multiverse would contain staggering diversity, with most bubbles hostile to life, but some, like ours, having conditions allowing complexity and observers. The quantum multiverse offers yet another perspective, suggesting reality consists of constantly branching parallel worlds representing all possible outcomes of quantum processes. This multiverse is not spatially separated, but layered upon our own space through quantum superposition. Every possible quantum history is realized in some branch, creating vast diversity not through spatial separation, but through quantum branching. These scenarios are not necessarily exclusive. The universe might be infinite, with unusual topology in regions beyond our observation. Eternal inflation might occur, creating bubbles that each contain quantum branching. The full structure of reality might be far more complex than any single model suggests, combining spatial extension, multiple bubble universes, quantum branching, and perhaps aspects we haven't imagined. What unites all these possibilities is their remoteness from direct verification. We can observe hints, test theories that make predictions about what lies beyond, constrain possibilities through precise measurements. But we cannot observe beyond the cosmic horizon. We cannot visit other bubbles. we cannot access other quantum branches. These regions remain forever beyond our observational reach, knowable only through theoretical reasoning and indirect inference. This limitation is not technological but fundamental. No improvement in telescopes, no advance in measurement techniques can let us see beyond the cosmic horizon created by finite light speed and cosmic expansion. We can never build a spacecraft to reach other bubble universes. Inflation ensures they recede faster than we can travel. We cannot observe other quantum branches. They're defined by their non-interaction with ours. What lies beyond the observable universe will remain beyond observation. Period. Yet this does not mean the question is meaningless or that speculation about it is pointless. These are predictions of our best theories, theories developed to explain what we do observe. If those theories are correct, their implications about unobservable regions are as valid as their explanations of observable phenomena. We can reasonably believe that galaxies exist beyond our horizon because the same physics that explains galaxies we see predicts their continuation. We can take seriously the possibility of eternal inflation because inflation solves real problems in cosmology, and eternal inflation follows naturally from inflation plus quantum mechanics. We can consider the many worlds interpretation because it offers solutions to genuine puzzles in quantum foundations. Moreover, the question of what lies beyond our observation connects to deep human drives to understand reality in its totality, not just the portion we can directly access. Throughout history, humans have always wondered what lies beyond the horizon, whether that meant distant lands before global exploration, other planetary systems before exoplanet detection, or the far future and deep past before modern cosmology. Often, these beyond the horizon regions eventually became accessible through technological progress or theoretical insight. In the case of the cosmic horizon, direct access will never come. But theoretical understanding might still deepen. Future developments in physics might provide stronger constraints on what's possible beyond our observation. Quantum gravity, if we achieve a complete theory, might reveal why certain vacuum states are preferred, or whether eternal inflation truly occurs. Better understanding of cosmological initial conditions might tell us whether the universe is finite or infinite. Advances in quantum foundations might clarify whether the many worlds interpretation is correct. The question also serves an important role in defining the limits of empirical science and clarifying the relationship between theory, observation, and belief. By confronting a case where our best theories make definite predictions about permanently unobservable regions, we're forced to articulate what we mean by scientific knowledge and how confident we can be in theoretical extrapolations beyond observation. These methodological clarifications benefit science generally, not just cosmology. Furthermore, even if we cannot observe other bubbles or regions beyond our horizon, their possible existence has implications for how we think about our own place in the universe. If countless other bubbles exist with different properties, and we exist in one that happens to allow life through anthropic selection, this affects how we interpret the apparent fine-tuning of physical constants. If the universe is infinite with endless repetition, this impacts how we think about identity, uniqueness, and meaning. If reality consists of branching quantum worlds, this influences our understanding of probability, choice, and the nature of possibility. These implications extend beyond physics into philosophy, touching on questions humans have contemplated for millennia. Are we alone in the universe? Is our existence significant, or merely one realization among infinite possibilities? Is the universe designed for life, or merely one outcome of natural processes that also produce countless lifeless wastes? What is the relationship between the actual and the possible? These ancient questions receive new articulation in light of modern cosmology and its implications about what lies beyond observation. The mystery of what lies beyond the observable universe also exemplifies the human capacity for abstract reasoning and theoretical exploration. We can never visit those regions, never receive a photograph or spectrum, never send a probe. Yet through mathematics, physics, and reasoning, we can construct sophisticated theories about them, constrain their properties, and engage in informed speculation. This represents a triumph of human intellect, the ability to reason rigorously about things forever beyond direct experience. It's worth reflecting on how remarkable it is that creatures evolved on one planet, orbiting one star in one galaxy, can figure out that the universe extends vastly beyond what they can observe, can estimate minimum sizes for that unobservable realm, can propose specific testable theories about its nature, and can engage in productive scientific discourse about it. This speaks to the power of scientific methodology, mathematical reasoning, and theoretical physics to transcend the limits of direct observation. At the same time, we must acknowledge the genuine possibility that we're wrong about fundamental aspects of what lies beyond. Our theories, successful as they are approximations based on limited observations within a tiny corner of existence. We assume the laws of physics are universal, that the cosmological principle holds at all scales, that our mathematical models capture cosmic reality. These assumptions have proven reliable within the observable universe, but extrapolating them arbitrarily far requires a leap of faith grounded in theoretical elegance and empirical success rather than direct verification. History shows that our understanding of the universe has been repeatedly revolutionized by new observations and theoretical breakthroughs. Before the 20th century, nobody imagined cosmic expansion, the Big Bang, or the quantum mechanical nature of reality. Before the late 1990s, we didn't know about dark energy or accelerating expansion. Each discovery changed our view of the cosmos. What future discoveries might await that would transform our understanding of what lies beyond our observation? Perhaps quantum gravity will reveal that space itself has properties we haven't imagined, changing predictions about what exists at vast scales. Perhaps new observations will detect unexpected patterns pointing to physics beyond our current theories. Perhaps philosophical or mathematical insights will clarify which of the various multiverse scenarios, if any, make sense. Or perhaps the question will remain forever open, a permanent mystery at the boundary of human knowledge. This permanent mystery need not be seen as a failure or limitation, but rather as an appropriate manifestation of the universe's vastness and richness. That reality extends beyond what any observer can see, that existence transcends experience, that the cosmos contains regions forever hidden from any particular vantage point. These are almost prerequisites for a universe with the grandeur and scope we observe even in the limited region accessible to us. In the end, what lies beyond the observable universe encompasses multiple types of beyond. There is the spatial beyond of regions too distant for light to have reached us. There is the causal beyond of bubble universes separated by eternally inflating space. There is the quantum beyond of parallel branches representing different outcomes of quantum processes. There is the conceptual beyond where our current theories reach their limits and speculation begins. And there is the epistemological beyond where empirical science encounters the boundaries of what can be known through observation. Each of these beyonds invites different responses, the spatial beyond seems most clearly amenable to scientific reasoning. We can reasonably infer that more galaxies exist beyond our horizon based on observed uniformity. The causal beyond of eternal inflation follows from well-motivated theories, but strains testability. The quantum beyond depends on interpretational choices in quantum mechanics. The conceptual beyond invites theoretical speculation constrained by mathematical consistency and compatibility with observation. The epistemological beyond forces us to confront questions about knowledge, existence, and the proper scope of science that may lack definitive answers. Together, these beyonds constitute perhaps the deepest mystery in cosmology. Not just what lies beyond the observable universe in spatial terms, but what it means for something to lie beyond observation, how we can reason about it, and what implications it has for understanding our place in existence. This mystery sits at the intersection of physics, philosophy, mathematics, and human curiosity about the nature of reality. We began by explaining the cosmic horizon, the observational boundary created by finite light speed and cosmic age. We explored how expansion creates this limit, carrying distant regions away faster than light can cross the expanding space between. We discussed what we can reasonably infer must exist beyond. At minimum, more galaxies and structure similar to what we observe, extending the patterns we see within our cosmic sphere. We examined how the cosmological principle suggests the universe has no special locations, implying similar conditions throughout regions we cannot observe. We considered what cosmic microwave background measurements tell us about the universe's minimum size, indicating it must be vastly larger than the observable portion and possibly infinite. We explored the strange implications of an infinite universe, including inevitable repetition of any finite configuration. We discussed alternative topologies that would make the universe finite yet unbounded, avoiding the repetition problem while remaining consistent with observations. We ventured into more speculative territory with eternal inflation and its prediction of bubble universes, each potentially with different physical properties drawn from the string theory landscape. We examined how anthropic reasoning might explain apparent fine-tuning if countless universes exist with varied properties. We considered the quantum multiverse of the many worlds interpretation, adding another layer of parallel realities to the spatial structure. We addressed challenges to the scientific status of claims about unobservable regions, exploring debates about testability and the proper boundaries of science. We discussed how future observations might indirectly constrain possibilities, even if direct observation remains forever impossible. We looked forward to the far future when cosmic expansion will shrink the observable universe, hiding evidence of cosmic history from future observers. And we reflected on philosophical questions about existence, information, and reality raised by permanently unobservable regions. Throughout this exploration, certain themes recur. The universe is almost certainly vastly larger than the region we can observe, perhaps infinitely so. The laws of physics likely operate throughout these unobservable regions, though different domains might realize different solutions to fundamental equations. Our observable universe represents one region of a possibly infinite and diverse reality, special to us, but not fundamentally different from countless other regions we can never see. The question of what lies beyond our horizon challenges our understanding of knowledge, existence, and the scope of scientific inquiry. What lies beyond the observable universe remains, ultimately, a mystery. Not the sort of mystery that might be solved next year or next century with better telescopes or cleverer experiments, but a permanent feature of our epistemic situation, a necessary consequence of being finite observers in what appears to be an infinite, or at least vastly larger reality. We can constrain this mystery through observation and reasoning. We can develop sophisticated theories that make predictions about it. We can engage in informed speculation grounded in our best physics and mathematics. But we cannot eliminate the mystery entirely. We cannot achieve complete knowledge of what lies beyond the horizon of observability. Perhaps this is as it should be. The universe is under no obligation to make itself completely comprehensible to human observers. That we can understand as much as we do, that we can reason coherently about regions we can never see, that we can construct mathematical models describing the cosmos at scales vastly exceeding human experience already represents an extraordinary achievement of science and human intellect. The mystery of what lies beyond serves as a humbling reminder that reality extends vastly beyond immediate experience, that our knowledge, however sophisticated, remains bounded, and that the universe contains depths we will never fully plumb. Yet this mystery also inspires. It points toward the infinite, the vast, the forever unknown. It suggests that existence is richer and stranger than any finite mind can grasp. It motivates continued exploration and theorizing, knowing that even if we cannot observe everything, we can refine our understanding and appreciate more deeply the magnificent scope of the cosmos. It invites wonder at a universe so large that most of it lies forever beyond our sight, yet whose visible portion alone contains trillions of galaxies, countless stars, and at least one species evolved to contemplate what lies beyond the boundary of the observable. The question of what lies beyond the observable universe represents cosmology at its most profound, science at its most ambitious, and human curiosity at its most fundamental. It exemplifies our drive to understand not just our immediate environment, but the totality of existence, to push understanding to its limits and peer beyond even when direct observation proves impossible. In grappling with this question, we define the scope and limits of scientific knowledge, confront deep philosophical puzzles about reality and observation, and exercise uniquely human capacities for abstract reasoning about the unobservable. What lies beyond the observable universe? More universe, almost certainly. How much more? Possibly infinite. With what properties? Perhaps the same as here, perhaps radically different in distant regions or other bubbles. Can we ever know for sure? Not through direct observation, but perhaps through increasingly refined theory and indirect inference. Does it matter? Scientifically, philosophically, and existentially? Yes. It matters for understanding the full nature of reality, for interpreting our place in existence, and for appreciating the magnificent scope of the cosmos we inhabit. This question, this mystery, this boundary between the known and the forever unknowable, stands as a monument to both the power and limits of human understanding. It reminds us that we are small, finite beings in an apparently infinite cosmos, yet beings capable of reasoning about that infinity, theorizing about its properties, and finding meaning in the exploration even when complete knowledge remains eternally out of reach. In contemplating what lies beyond the observable universe, we engage with the deepest mysteries of existence itself, exercising our highest capacities while acknowledging our inevitable limitations, reaching always toward truth, knowing we can never grasp it completely, yet finding value and purpose in the eternal reaching. The profound implications of what lies beyond our observable universe extend into territories that challenge not just our scientific understanding, but our philosophical frameworks for making sense of reality itself. When we consider that the vast majority of existence may be forever hidden from us, we must reconsider fundamental assumptions about knowledge, causality, and the relationship between observation and reality that have guided scientific thinking for centuries. One aspect worth exploring in greater depth is the mathematical structure underlying our theories about the unobservable universe. Mathematics has proven remarkably effective at describing physical reality, a phenomenon physicist Eugene Wigner famously called the unreasonable effectiveness of mathematics in the natural sciences. Within the observable universe, we can test mathematical predictions against empirical measurements, verifying that our equations accurately capture physical behavior. But when we extrapolate those same equations to regions beyond observation, we're making a profound assumption that mathematical relationships observed here continue to hold there. This assumption isn't arbitrary. It's grounded in the remarkable consistency we observe in physical laws across vast distances and times. The same quantum mechanics that describes atoms on Earth also explains the spectra of distant quasars billions of light years away. The same gravity that keeps planets in orbit around our Sun also governs the dynamics of galaxies at the edge of the observable universe. The same nuclear physics that powers our Sun also powered stars in the early universe over 13 billion years ago. This universality of physical law, confirmed again and again within our observational reach, provides strong justification for believing it extends beyond. Yet, we must acknowledge that this universality itself requires explanation. Why should the laws of physics be the same everywhere? One answer comes from the principle of relativity. The laws of physics shouldn't depend on where or when you are, because there's no absolute reference frame against which to define where or when. This principle has guided physics since Einstein and has proven enormously fruitful. But it's ultimately an assumption, one that could, in principle, be violated in regions far beyond our observation. The inflationary multiverse scenario actually predicts that physical laws might vary between different bubble universes, each bubble representing a different vacuum state with potentially different effective laws. This doesn't violate relativity within any given bubble. The laws remain uniform throughout each bubble's extent, but between bubbles, the fundamental constants and perhaps even the particle content and forces could differ. In this scenario, the universality of physical law holds within each causally connected region, but breaks down across the full, inflating multiverse. This raises an interesting question about what we mean by physical law. Are the most fundamental laws the mathematical structures that govern all possible universes, like the equations of string theory or some deeper theory, which might admit many different solutions? Or are physical laws the specific rules that operate in our particular bubble or region? Rules that might be contingent rather than necessary. This distinction matters for how we think about what lies beyond our observation. If physical laws are the deep mathematical structures admitting multiple solutions, then those structures likely operate throughout the multiverse, even if different regions realize different solutions. We could reason about other bubbles using the same mathematical framework that describes our own, even though specific details differ. But if physical laws are simply the regularities we observe in nature, which might differ elsewhere, then reasoning about beyond horizon regions becomes more speculative. String theory offers one possible framework for thinking about this. The theory proposes that at the deepest level, reality consists of vibrating strings in a higher dimensional space, with apparent particles and forces emerging from different vibration modes and the geometry of compactified dimensions. String theory itself would be the universal law, operating throughout any possible universe. But the specific vacuum state, the particular compactification geometry, could vary between regions, leading to different effective physics. In this picture, we could use string theory to reason about other bubbles, even though we can't observe them. We could calculate which vacuum states are mathematically possible, estimate which might be more probable based on dynamics of compactification, and predict the effective physics that would result. These predictions wouldn't tell us which specific vacuum state any particular other bubble occupies, but they would constrain the possibilities and provide a framework for informed speculation. Of course, string theory itself remains unconfirmed, and even if correct, our understanding of it remains incomplete. We don't know how to calculate reliably from first principles which vacuum states are more likely, or how transitions between states occur during bubble formation. The landscape of possibilities might be even larger than current estimates suggest, or smaller, or structured in ways we haven't imagined. Nevertheless, the framework illustrates how we might reason about unobservable regions using mathematical structures that extend beyond immediate empirical verification. Another deep question concerns the nature of probability in a universe or multiverse containing regions we cannot observe. Within standard physics, probability describes our uncertainty about outcomes. When we say a quantum measurement has a 50% chance of yielding spin-up, we mean that in an ensemble of identically prepared systems, roughly half yield spin-up. We can test this by repeated measurements, verifying that predicted probabilities match observed frequencies. But what does probability mean when applied to unobservable regions? If eternal inflation predicts that bubbles with certain properties are probable, what does this probability signify if we can only ever observe one bubble, our own? We can't perform repeated trials where the multiverse is generated many times to see what fraction of bubbles have various properties. The ensemble of bubbles all exists in the one actual multiverse, but we can only observe our particular bubble. Some physicists argue that, in such cases, probability should be interpreted anthropically. The probability we should consider is the conditional probability of our observations given that we exist as observers. On this view, it doesn't matter how many bubbles of various types exist in the multiverse. What matters is the fraction of observers who find themselves in bubbles with our observed properties. This shifts probability from being about frequencies of bubble types to frequencies of observer moments. But this anthropic probability faces its own puzzles. How do we count observers? Do we weight by number of individuals, by total observer moments throughout history, by some measure of consciousness or self-awareness? Different counting measures give different results. Moreover, if the multiverse is infinite and contains infinitely many observers of various types, how do we make sense of ratios between infinities? These measure problems in cosmology have occupied considerable attention from theoretical physicists, and no consensus solution has emerged. They highlight that extending probabilistic reasoning to multiverses containing unobservable regions isn't straightforward. Our standard frameworks for thinking about probability, developed for finite ensembles or repeatable experiments, strain when applied to unique, infinite, or unobservable scenarios. Related to this is the question of explanation itself. Science seeks not just to describe what we observe, but to explain why it is so. Good explanations unify diverse phenomena, reveal underlying principles, make accurate predictions, and provide understanding. But what constitutes a good explanation when the explanatory framework invokes unobservable entities? Consider the anthropic explanation for fine-tuning. The fundamental constants of our universe appear to be finely tuned for life. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the electromagnetic force were slightly different, complex chemistry might be impossible. If the strong force were tuned differently, stable atomic nuclei might not exist. These apparent coincidences cry out for explanation. The multiverse provides one. If countless bubbles exist with all possible combinations of constants, then some bubbles inevitably have life-friendly values, and we necessarily observe one of those bubbles because we couldn't exist otherwise. This explains the apparent fine-tuning without invoking design or needing deeper principles that fix the constants to their observed values. Critics object that this isn't really an explanation because it can't be tested. We can't observe other bubbles to verify they exist with different constants. The multiverse explanation makes our universe seem typical among life-friendly universes, but we have a sample size of exactly one. Moreover, the explanation seems to work too well. It could explain any observation whatsoever by claiming that universe happens to be the one we observe because we're here. This risks becoming unfalsifiable and therefore unscientific. Defenders respond that the multiverse isn't invented to explain fine-tuning. It's predicted by independently motivated theories like eternal inflation. The anthropic reasoning then applies this predicted multiverse to explain observations that would otherwise remain puzzling. Furthermore, the explanation does make some predictions. If fine-tuning is anthropically explained, we should expect to find ourselves in a universe that's not too much more life-friendly than necessary. Since universes barely meeting life's requirements should vastly outnumber those exceeding requirements. We can test this by examining how much further various constants could be changed while still allowing life. This debate illustrates how reasoning about unobservable regions challenges our understanding of scientific explanation. We're forced to clarify what we demand of explanations, how heavily we weight testability versus theoretical coherence, and whether explanations invoking unobservable entities can ever be satisfactory. Let us delve deeper into the specific physical mechanisms that create and maintain the boundary between observable and unobservable regions. The cosmic event horizon isn't a static structure, but a dynamical feature of an expanding universe. Understanding its behavior requires engaging with general relativity and cosmological models at a detailed level. In a universe dominated by dark energy, as ours appears to be, the expansion rate asymptotically approaches a constant value called the Hubble constant. This creates a horizon at a fixed proper distance, roughly 16 billion light-years in our universe's future. Galaxies currently beyond this distance will never become visible to us, no matter how long we wait, because light they emit now will never overcome the expansion of space to reach us. Conversely, galaxies currently within this horizon, but sufficiently distant, will eventually slip beyond it as expansion carries them away. The mathematics describing this involves the scale factor, which quantifies how distances between objects change with time in an expanding universe. In a dark, energy-dominated universe, the scale factor grows exponentially, meaning distances increase by a fixed percentage per unit time, rather than by a fixed amount. This exponential growth ensures that once an object crosses beyond the horizon, it can never return to observability. Interestingly, the cosmic event horizon differs from the particle horizon, which defines the observable universe as we typically discuss it. The particle horizon represents the maximum distance from which light could have traveled to reach us since the Big Bang, accounting for expansion. The event horizon represents the maximum distance from which light emitted now could ever reach us in the infinite future. In a dark, energy-dominated universe, the particle horizon continues growing, though increasingly slowly, while the event horizon approaches a fixed size. This means that very distant galaxies we can see today, galaxies whose light left them billions of years ago and has reached us after traversing expanding space, are now beyond the event horizon. We can see them because we're observing their past, when they were within our past light cone. But if they emit light now, that light will never reach us. They've crossed beyond our event horizon, even though they remain within our particle horizon. Understanding these distinctions helps clarify what we mean by beyond the observable universe. Do we mean beyond the current particle horizon, beyond the event horizon, or beyond where light emitted now will ever reach? Each definition includes different regions and has different implications. Most commonly, when discussing the observable universe, we mean the particle horizon region from which light has had time to reach us since the Big Bang. The physics determining horizon sizes connects intimately to the energy content of the universe. In the early universe, dominated by radiation, the particle horizon grew rapidly in comoving coordinates. During matter domination, which prevailed from about 50,000 years after the Big Bang until a few billion years ago, the horizon grew more slowly. Now, in the dark energy-dominated era, the particle horizon grows slowly toward a finite limiting size, while the event horizon has already reached approximately its final value. These different expansion eras affect not just horizon sizes, but also what lies beyond them. Regions beyond our horizon, but within the horizon of other observers, may be in different expansion eras if they're at vastly different cosmic times due to light travel time. This creates a complex structure where different observable universe regions are seeing different cosmic epochs in the regions they can observe. The thermal history of the universe also matters. The cosmic microwave background originates from the surface of last scattering, when the universe cooled enough for electrons and protons to combine into neutral hydrogen, making space transparent. Before this recombination, the universe was an opaque plasma through which light couldn't travel freely. This places an ultimate limit on how far back we can see with electromagnetic radiation, regardless of telescope technology. However, other messengers might penetrate further. Neutrinos decoupled from matter when the universe was only about 1 second old, creating a cosmic neutrino background analogous to the cosmic microwave background. If we could detect these primordial neutrinos, we could observe the universe at earlier times. Similarly, gravitational waves propagate freely through matter and radiation, potentially carrying information from the very earliest moments after the Big Bang, possibly from inflation itself. Future detectors sensitive to these exotic messengers might push back the observational boundary, revealing earlier cosmic epochs. But they cannot overcome the ultimate horizon imposed by inflation and expansion. Before inflation, any regions that underwent inflation became exponentially separated, creating separate bubble universes. No information can cross between bubbles because the inflating space between them grows too rapidly. This represents an absolute information boundary, not just a practical one. Within our bubble, though, improved sensitivity to primordial gravitational waves or the neutrino background could provide information about larger cosmic scales. Features imprinted during inflation might carry information about the total size or topology of space. This wouldn't let us see beyond our observable region, but it could constrain how much further space extends. The question of what information, in principle, might be extractable about beyond horizon regions through any physical means touches on deep issues in quantum gravity and holography. Some proposals in quantum gravity, particularly those based on the holographic principle, suggest that information about a volume of space is encoded on its boundary. If true, This might imply that information about beyond horizon regions is somehow encoded in physical degrees of freedom at or near our horizon, even though we cannot directly observe those regions. The holographic principle originates from black hole thermodynamics, where the entropy of a black hole is proportional to its surface area rather than its volume, suggesting that the information content of a region is determined by its boundary rather than its interior. Extending this to cosmology is speculative, but some theorists propose that the information content of the universe is encoded on the cosmic horizon. This wouldn't let us see beyond the horizon in a conventional sense, but it might mean that complete information about physics within our observable region implicitly constrains what lies beyond. These ideas remain highly speculative and controversial. They represent attempts to extend quantum information theory and quantum gravity to cosmological contexts in ways that might yield new insights into the observable-unobservable boundary. Whether such extensions prove fruitful remains to be seen, but they illustrate that the question of what lies beyond observation continues to motivate new theoretical frameworks. Let us turn to more philosophical territory and examine what the existence of unobservable regions implies for various philosophical positions about the nature of reality and knowledge. The correspondence between our theories and unobservable reality has been a central concern in philosophy of science for over a century. Scientific realism, the view that successful scientific theories accurately describe real features of the world, including unobservable entities, faces challenges from permanently unobservable regions. Realists argue that we should believe theories not just because they successfully predict observations, but because they're true or approximately true descriptions of reality. Electrons, quarks, and curved spacetime are real, not just convenient fictions, because theories invoking them successfully explain and predict phenomena. Extending this to beyond horizon regions seems natural for realists. If general relativity successfully describes gravity throughout the observable universe, realists say we should believe it describes gravity beyond the horizon too. If inflation successfully explains observable features of the cosmic microwave background, we should believe the unobservable bubble universes it predicts really exist. The theories make no distinction between observable and unobservable regions. They describe reality as a whole. But anti-realists and empiricists object that we can only ever justify belief in theories based on observable consequences. Theoretical claims about permanently unobservable regions go beyond what evidence can support. We might accept theories as empirically adequate, saving the phenomena we observe, without believing their claims about unobservable reality. Perhaps eternal inflation is just a useful mathematical framework for understanding our observable universe, not a description of actually existing other bubbles. This debate isn't easily resolved, partly because it's not clear what would count as resolving it. Both positions are logically consistent and compatible with all possible observations. The choice between them rests on philosophical commitments about parsimony, theoretical elegance, the aims of science, and the relationship between truth and empirical adequacy. A related philosophical question concerns the modal status of physical laws. Are the laws of physics necessary, holding in all possible universes, or contingent, true of our universe but possibly different elsewhere? If laws are necessary, then what lies beyond our observation must obey the same laws we observe here. But if laws are contingent, different regions might operate by different principles. The multiverse scenarios we've discussed suggest laws, or at least their specific form, are contingent. Different bubbles realize different vacuum states with different effective laws. This challenges traditional views in philosophy of science that treat laws as universal and necessary. It suggests that what we call physical laws might be more like local regularities, true throughout large regions, but not absolutely universal. However, there might be deeper laws governing the full multiverse, the equations of string theory, or some more fundamental theory that describes how different vacuum states arise and how bubbles form. These deeper laws might be necessary and universal, with contingency appearing only at the level of effective laws within particular bubbles. This would preserve a notion of universal law while accommodating diversity across the multiverse. The question connects to metaphysical debates about the nature of laws. Are laws fundamental features of reality that govern how things behave? Or are they just descriptions of patterns we observe in nature? If the former, then the same fundamental laws might govern all of reality, including beyond horizon regions, even if they manifest differently in different contexts. If the latter, then laws are just our summaries of local regularities that might not apply elsewhere. These abstract philosophical questions have concrete implications for how we think about cosmology and the legitimacy of extrapolating known physics to unknown regions. They force us to examine the foundations of scientific reasoning and clarify what justifies extending theories beyond their observational basis. Another philosophical dimension concerns personal identity and the existence of duplicates in an infinite universe. If exact copies of you exist in distant regions beyond the horizon, what does this mean for identity and uniqueness? Are those duplicates really you, or merely qualitatively identical but numerically distinct individuals? Most philosophical theories of personal identity would say they're distinct individuals. Psychological continuity theories, which ground identity in continuous chains of memories and personality, would say your duplicate isn't you because there's no continuous psychological connection between you and them. They're a separate person who happens to have identical memories and personality. Physical continuity theories, which ground identity in continuous physical existence, would say the duplicate isn't you because it's a spatially separate body with no physical continuity to yours. Yet, the existence of such duplicates challenges our intuitions about uniqueness and significance. If infinitely many exact copies of you exist throughout the universe, making all the same choices and having all the same experiences, does this diminish your individuality or the meaning of your experiences? Most philosophers would say no. Your experiences have meaning to you regardless of whether duplicates exist elsewhere having identical experiences. The fact that others might experience the same things doesn't make your experiences less real or valuable. Still, the possibility is unsettling. It suggests that nothing about you is unique, that every possible version of you exists somewhere, that every choice you make is also made differently by some duplicate in some distant region. This challenges our sense of free will and agency, even though, philosophically, those duplicates' choices don't determine yours. In the quantum multiverse of many worlds, similar issues arise. If every possible outcome of your choices is realized in some branch, are you identical to your counterparts in other branches? Are all those branches equally real? Do you have a special relationship to your past selves in other branches? Or are they as other to you as distinct individuals? These questions don't have clear answers. They push the boundaries of personal identity theory into strange territory where our intuitions, evolved for thinking about single individuals in a single world, struggle to apply. Yet, they're not merely philosophical thought experiments. They're potential consequences of taking our best cosmological and quantum theories seriously. The ethical implications also deserve consideration. If every possible version of your life is realized somewhere in the multiverse, does this affect moral responsibility? If you make a good choice, but some duplicate makes a bad choice, are you still praiseworthy? Presumably yes, because you control only your own choices, not those of duplicates. Each person remains responsible for their own actions, regardless of what duplicates do elsewhere. But the existence of duplicates might affect consequentialist moral reasoning. If every possible outcome occurs somewhere, does the outcome of your particular choice matter less? Arguably not. You should still aim for good outcomes in your branch or region, since those outcomes matter to the beings affected by them. The fact that bad outcomes occur elsewhere doesn't diminish the importance of preventing them where you can. These ethical considerations remain speculative, as we don't know whether duplicates or many worlds branches really exist. But they illustrate how cosmological theories about what lies beyond observation can connect to fundamental questions about value, meaning, and how we should live. The anthropic principle, discussed earlier in the context of fine-tuning, deserves deeper exploration. There are actually several forms of the anthropic principle with different implications. The weak anthropic principle merely notes that our observations are necessarily biased by the requirement that conditions allow observers to exist. We shouldn't be surprised to find ourselves in a region of space and time where life is possible, because we couldn't exist elsewhere. The strong anthropic principle makes a bolder claim. The universe must have properties allowing life to develop, because otherwise, there would be no observers. Some versions of this principle verge on teleology, suggesting the universe is somehow directed toward producing observers. Most physicists reject these stronger forms as unscientific and unnecessary. In a multiverse context, the weak anthropic principle becomes a powerful explanatory tool. We observe life-friendly conditions, not because all conditions are life-friendly, but because only life-friendly regions contain observers. This explains apparent fine-tuning without invoking design or teleology. However, it requires the multiverse to be real. Otherwise, the principle just postpones, rather than answers the question of why our universe has life-friendly properties. The anthropic principle also makes some testable predictions, though these are controversial. If our universe's properties are anthropically selected from a landscape of possibilities, we'd expect to find ourselves in a typical life-friendly universe, not an unusually optimal one. This suggests that constants should be near the boundaries of life-friendliness, barely good enough rather than far better than necessary. We can test this by examining how much various constants could change while still allowing life. Some constants do appear to be near boundaries. Slightly different values would preclude stars, complex chemistry, or sufficient time for evolution. Others seem to have more room for variation. Whether this pattern supports anthropic reasoning remains debated. Critics note that we don't have a precise definition of which conditions allow life, making it hard to determine what counts as barely sufficient versus excessive optimization. Furthermore, anthropic reasoning sometimes produces paradoxes. The doomsday argument, for instance, uses anthropic reasoning to predict humanity's extinction will occur relatively soon, based on the idea that we should expect to be typical observers among all humans who ever live. If humanity lasts millions of years with trillions of people, we'd be unusually early observers, which seems improbable. Therefore, the argument concludes, humanity probably won't last that long. Most reject this reasoning, but explaining exactly what's wrong with it proves difficult. It highlights that anthropic reasoning can lead to counterintuitive conclusions and must be applied carefully. Similar paradoxes arise when considering observer populations in the multiverse, reinforcing the measure problem discussed earlier. Despite these challenges, the anthropic principle remains one of our few tools for reasoning about multiverse scenarios. If countless bubbles exist with varied properties, anthropic selection offers a framework for predicting what we should observe, given that we're observers in some bubble. Whether this constitutes genuine scientific reasoning or venturing into metaphysics depends on your philosophical stance toward multiverses and unfalsifiable claims. Let us return to the concrete physics of cosmic horizons and explore what existing and future observations might reveal. While we cannot directly observe beyond the horizon, indirect signatures might provide evidence for or against various scenarios about what lies there. The cosmic microwave background polarization holds particular promise. The CMB polarization comes in two types: E mode, caused by density perturbations, and B mode, which can be produced by gravitational waves from inflation. Detecting primordial B mode polarization would provide strong evidence for inflation and might reveal details about the inflationary potential, constraining how inflation proceeded and whether eternal inflation results. Several experiments are currently searching for these primordial B modes, including ground-based telescopes like BICEP and SPT, and proposed satellite missions. The signal is extremely faint and easily confused with foregrounds from galactic dust and lensing of E-mode polarization. But if detected and confirmed, it would revolutionize our understanding of the early universe and support theoretical frameworks predicting bubble universes and eternal inflation. Additionally, the cosmic microwave background contains subtle features that might indicate unusual topology or departures from simple, infinite flat geometry. If the universe wraps back on itself with a topology smaller than, but comparable to our observable region, we might see correlated temperature patterns where we observe the same structures from different directions. Searches for such patterns have found no convincing evidence, but continued analysis with better data might reveal signatures indicating finite volume or exotic topology. The large-scale structure of the universe provides another probe. The distribution of galaxies reflects the initial density perturbations from the early universe, amplified by gravity over billions of years. By mapping billions of galaxies, surveys like SDSS, DESI, and future projects can reconstruct the initial perturbation spectrum at large scales. Any features in this spectrum, influenced by physics operating on scales larger than our observable universe, might appear as anomalies or patterns in the galaxy distribution. Some cosmologists have reported potential anomalies in the CMB at the largest observable scales, including an apparent alignment of low multipole moments and unexpected power suppression. While these might be statistical flukes or systematic errors, they could potentially indicate that the universe is finite, has unusual topology, or experienced physics beyond simple inflation. Further observations and analysis are needed to determine whether these features are real and, if so, what they imply. Gravitational wave astronomy opens entirely new windows. While current detectors like LIGO observe waves from stellar mass black holes and neutron stars, future space-based detectors like LISA will probe different frequency ranges, potentially detecting gravitational waves from the early universe. A background of primordial gravitational waves would carry information about cosmic inflation imprinted directly on space-time itself, providing a unique probe of the universe's earliest moments. If we detect primordial gravitational waves, their spectrum and characteristics would constrain inflation models, potentially distinguishing between versions that lead to eternal inflation and those that don't. Features in the gravitational wave spectrum might even indicate the total size of the universe or whether it has unusual topology, though extracting such information would be extremely challenging. Particle physics experiments might contribute indirectly. If supersymmetry is discovered at the Large Hadron Collider or future accelerators, this would support string theory, which naturally incorporates supersymmetry. This wouldn't prove the string landscape exists or that eternal inflation occurs, but it would strengthen the theoretical framework predicting them. Conversely, if supersymmetry isn't found and string theory faces increasing empirical challenges, alternative frameworks might become more attractive. Dark energy studies are crucial. Understanding dark energy's properties, whether it's truly a cosmological constant or dynamical field that might vary with time or space, affects predictions about eternal inflation and the multiverse. If dark energy has specific properties indicating it occupies a particular vacuum state in a landscape, this would indirectly support the landscape picture. Measurements from supernovae, baryon acoustic oscillations, and weak gravitational lensing continue refining our knowledge of dark energy. None of these observations will directly show us what lies beyond the observable universe. That remains impossible. But they can test theories that make predictions about beyond horizon regions, providing evidence that makes various scenarios more or less plausible. Science progresses through such indirect inference regularly, building confidence in theories through cumulative successes across multiple domains. As we contemplate future observations, we must also acknowledge what will remain permanently beyond reach. Even with arbitrarily advanced technology, certain boundaries cannot be overcome. We cannot signal to or receive signals from beyond the cosmic horizon due to expansion. We cannot visit other bubble universes because inflation separates them insurmountably. We cannot observe other quantum branches because they're defined by non-interaction. These are not technological limitations, but fundamental features of the physics involved. This permanence of the observational boundary has implications for the far future of cosmology as a science. As mentioned earlier, in hundreds of billions of years, accelerating expansion will have carried all distant galaxies beyond the horizon, leaving future observers in an apparently empty universe. They would lack evidence for the Big Bang, cosmic expansion, or the existence of other galaxies. Cosmology, as we know it, would become impossible. Unless they have access to records from earlier times when more was observable, future observers would face fundamental limits on what they could learn about cosmic history and structure. They might develop incorrect cosmological theories based on their limited observations, confident in conclusions that are nevertheless wrong, because crucial evidence has literally expanded out of existence. This scenario has unsettling implications for our own situation. Are we like those future observers, missing crucial evidence that has already expanded beyond our reach? Have earlier cosmic epochs or structures that would revolutionize our understanding already passed beyond? Observability? We have no way to know for certain, but the possibility should inspire appropriate humility about our cosmological confidence. It also raises questions about the accumulation and preservation of knowledge. If crucial evidence becomes unobservable over time, then knowledge gained when it was observable becomes increasingly precious. Future civilizations, if they exist, will depend on records transmitted from earlier times to understand cosmic history. This gives cosmic timescales a directionality for knowledge accumulation. Some things become easier to know with time as we develop better instruments, but other things become harder or impossible to know as evidence recedes beyond observation. In our own time, we occupy a privileged moment, cosmologically speaking. The cosmic microwave background remains observable, carrying information about the early universe. Distant galaxies reveal cosmic history across billions of years. Evidence for inflation, dark energy, and large-scale structure remains accessible. We can observe the universe across vast spans of time and space, gathering data that future observers may lack. This makes our current efforts at understanding cosmology especially important. We may be among the last observers for whom comprehensive cosmological evidence remains available. Looking beyond this, we can speculate about hypothetical civilizations vastly more advanced than ours. Could a sufficiently advanced civilization extract more information about beyond horizon regions than we can? Might they develop technologies or physical theories allowing them to probe further? Within known physics, the answer appears to be no. The cosmic horizon imposed by expansion and inflation represents an absolute boundary, not just a practical one. No signal can cross it regardless of technology. However, if physics beyond general relativity and quantum mechanics exists, governing higher energies or shorter distances than we can currently probe, might such physics offer loopholes? Some speculative proposals exist. If wormholes could be created and stabilized, they might in principle allow connections between distant regions, potentially even between different bubble universes. Similarly, if extra dimensions exist as string theory suggests, travel through higher dimensional space might bypass ordinary spatial separation. However, these remain purely speculative, and most physicists doubt they're possible. General relativity generally forbids traversable wormholes without exotic matter with negative energy density, which probably doesn't exist. Extra dimensions, if real, are likely compactified to Planck scale sizes, far too small for travel. More realistically, advanced civilizations might develop better theoretical understanding, discovering deeper principles that constrain what lies beyond observation. Even if they cannot observe other bubbles, they might calculate from first principles which vacuum states can exist, how bubbles form, and what properties they typically have. This wouldn't reveal specific details about any particular beyond horizon region, but would constrain the possibilities through theoretical reasoning. Such civilizations would face the same fundamental limits we do regarding observability, but they might be much more confident in their theoretical frameworks through extensive testing across many observable domains. Just as we're more confident in general relativity than previous generations because we've tested it in more extreme conditions and to greater precision, future civilizations might test theories to such levels that extrapolations beyond observation become extremely reliable, even if never directly verifiable. Ultimately, though, what lies beyond the observable universe will remain, in important senses, mysterious and uncertain, regardless of technological or theoretical advances. This isn't a problem to be solved, but a feature of reality reflecting the finiteness of observers within an apparently infinite, or at least vastly extended cosmos. As we conclude this exploration, it's worth reflecting on what this mystery means for human understanding and our place in the universe. The question of what lies beyond our observation represents cosmology at its most profound. It pushes scientific reasoning to its limits, raises deep philosophical questions, and inspires both wonder and humility. We've explored multiple possibilities, simple continuation of more galaxies and structure, extending perhaps infinitely, exotic topologies, making the universe finite, yet unbounded, bubble universes in an eternally inflating multiverse, with potentially different physics, quantum parallel worlds branching from every possibility, and combinations of these scenarios creating reality of staggering complexity. We've examined the evidence suggesting the universe extends far beyond what we can see, the theoretical frameworks predicting different scenarios about what lies beyond, and the challenges of reasoning about regions we can never observe. We've considered implications for physics, philosophy, probability, identity, meaning, and the nature of scientific knowledge itself. Through all this, certain themes emerge. Reality extends vastly beyond immediate human experience. The universe is far larger, possibly infinitely so, than the region we can observe from our particular location in space and time. What we see represents a tiny fragment of existence, special to us, but not fundamentally different from countless other regions forever beyond our sight. Our theories, developed to explain observations within this fragment, naturally extrapolate beyond it. Whether these extrapolations accurately describe unobservable reality, we can never know with certainty, but they represent our best attempts to understand the cosmos as a whole. These theories suggest that what lies beyond is both similar and potentially different, similar in operating according to the same fundamental principles, potentially different in realizing different solutions to those principles. The mystery of what lies beyond our observation isn't a failure of science, but a testament to reality's vastness and to the limitations inherent in being finite observers. We can never observe everything, can never verify all aspects of our theories, can never achieve complete knowledge of all existence. This is both humbling, reminding us of our smallness and finitude, and ennobling, showing that we can reason about and partially understand realities we can never directly experience. This exploration exemplifies humanity at its most ambitious and reflective. We use mathematics, physics, observation, and reasoning to transcend immediate experience, inferring the existence of realms we'll never see, contemplating possibilities we can never verify, pushing understanding to its limits and acknowledging those limits with appropriate humility. We engage with the deepest questions about existence while recognizing that some questions may forever lack definitive answers. What lies beyond the observable universe? We've explored this question from multiple angles: scientific, philosophical, mathematical, and speculative. We've seen that while we cannot answer definitively, we can constrain possibilities, test relevant theories, and engage in informed reasoning about the unobservable. This represents both the power and limits of human understanding, our capacity to know much while accepting that much remains and will always remain mysterious. In the end, this mystery invites not despair, but wonder. A universe so vast that most of it lies forever beyond our sight is a universe worthy of our highest efforts to understand and appreciate. That we can contemplate what lies beyond the boundary of observation, reason about it coherently, and recognize both what we can and cannot know about it speaks to the remarkable capacities of conscious beings evolved on one small planet to understand something of the cosmos they inhabit, while acknowledging that cosmos extends infinitely or nearly so beyond their grasp, forever mysterious in its full extent, yet partially knowable through science, mathematics, and thought. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.